All right, so let's start. Uh, okay, all right. So in this crazy world of 370, we've been designing adder subtractor ICs, right? We've been taking examples of taking numbers and adding and subtracting. So we said that we want to design a custom IC, which will remember this example, which will read numbers A, B, C, D, add them up, right? And another case, we said, well, you may want to read the numbers, do A plus B plus C minus D. In another case, you may want to read numbers, do A plus B minus C minus D. The point is not that we are very much interested in addition or subtraction. The point is that depending on different applications, you may want a dedicated digital IC which performs the task that you wish for your application. Right, and so what you want is a custom IC, an IC dedicated to your particular solution. Now, the alternative to that is, as I said, there are a variety of general purpose ICs available. You take them up and you connect them and customize it for your application. And the problem with that is the PCB space becomes large, weight and size becomes a problem. The delays are much longer, power dissipation will be higher. So all those issues are there, as a result of which you want to put everything inside one IC. So these are just, as I said, examples to illustrate that particular point. Now we have discussed this, that when you want to design an IC, the cost of an IC is actually, you can break it up into two parts. One is the recurring cost. Every time you fabricate, you have to use a wafer. You're using a part of a wafer, and so there is a die cost, and we had seen earlier there's a packaging cost, there is a test cost. That's a recurring cost, and then there is a one-time cost, non-recurring, and that one-time cost is, if we look at it, so production cost was die cost, packaging cost, and test cost here. The one-time cost is the cost of designing an IC, and we will just quickly see when you want to fabricate an IC, you need a set of masks to fabricate the IC. So for your IC, a set of custom designed masks are needed. So roughly, if we are taking 180 nanometer as an example, and so for 180 nanometer, there may be about somewhere between 20 to 30 masks required, and they may cost you, these numbers vary, they may cost you up to $100,000 for the entire masks to be made. So for your circuit, a custom set of masks will have to be made. They may cost you $100,000. Now, design cost. Now, there are two parts to a design cost. One is that all the design that you're seeing now, you'll appreciate, is done through a variety of CAD tools. It's done through a variety of CAD tools. These CAD tools are expensive, and you have to pay license fees. Right? So there is a CAD tool cost. And then, of course, you have to hire people to do the design, and there's a cost associated with paying the design engineers. So there's a cost associated with that. And as an example, I've taken design cost also as 100K. Okay, you can, let's say you have a 3-member team designing an IC. You can look at the average salary, let's say in India, average salary that you have to pay to a good design engineer, and you can calculate how much will be the let's say it's a 6-month project or a 1-year project, you can calculate how much cost will come. So you will see that these numbers are not too far off. Okay, so the development cost, this one-time cost, may be about $200,000. So now you can see here, if my application requires not too many ICs, let's say 1,000 pieces or so, the development cost divided by n, the first part here, itself becomes $200. So if I am a developer of some application and I require 1,000 pieces or 2,000 pieces or so, and I want a custom IC design, you can see that is just too expensive. First of all, it requires a certain expertise which is not commonly found. And, not everybody can design an IC, so that expertise is not there. And the other thing is if the volumes are low, the cost comes out to be 200 here. And so the point that I'm trying to make is custom design is economical only if volumes are, in millions. Because if you put here 10 to the power 6 here, then you know that the first cost becomes only $0.2. And eventually, as the volumes are large, this becomes less important, and the cost of the IC is determined by these factors that are there. So through this example, what I'm trying to tell you is that if you want a dedicated custom solution for your application and your volumes are low, you cannot afford it. You can't do that, okay? The cost is too high. So now the issue is the following. I don't want as I said, so what is the alternative then? If I don't have a custom IC, custom dedicated IC for my application, the other alternative is then, take up a lot of ICs and connect them up. So alternatives, okay, by the way, before I go on, and let me talk about a mask. What is this mask that I just talked about? So let's say you have a piece of silicon. You have a piece of silicon, right? This region is silicon here. And you want to create in the silicon a region which is N plus. You realize that MOS transistor consists of N plus source and N plus drain and all that, right? So you want to create a region which is N plus. Now note, I want N plus here. I don't want N plus here. I don't want N plus here. I want N plus to be done selectively at a certain place on my silicon IC. How would I do that? Very simply. Well, what I would do is I would take a piece of silicon and I'll deposit silicon dioxide on it. First, cover it up with silicon dioxide. Then what I'll do is I'll cover it up with a spin coat. It's a photoresist. It's a chemical which is sensitive to light. All right. So photoresist, I drop some solution and spin coat it and do some thermal treatment and all that. So we spin coat photoresist. Now this is where the mask comes in. So the mask has regions of transparent regions and opaque regions. So what I do is I shine UV light through this particular mask. The regions which are opaque, they will not get any light. The regions which are transparent, they will get exposed. Now what happens is the regions which are exposed, the chemical property changes of that particular photoresist, because it's a chemical whose properties depend on the light that is there. So you have to expose it for a certain time. So what happens is this region of the photoresist is different from this region, the exposed region here. So next what you do is you can remove this particular photoresist by putting it in certain chemicals. You can selectively remove this because this is different from this. Then what you can do is you can take hydrofluoric acid and etch away SiO2. You can etch away SiO2 also. So now what you can do is if you wish, you can remove the photoresist also. So what you end up with is getting silicon with silicon dioxide here and silicon dioxide here and no silicon dioxide here. Now you put it in a diffusion chamber or an ion implantation machine and you can create an N plus region. So you end up getting an N plus region in silicon here. But note that a series of steps are required. But what is essential to do all this, say a process engineer or a person who is involved in fabricating knows how to do silicon dioxide deposition, knows how to do N plus, knows all of those steps there. But you have to tell that particular person in which region do I want N plus. In which region? Because that N plus defines, later on we'll see 2 N pluses and all that define the transistor. So you have to tell where I want an N plus. Which means, basically where I want an N plus, how do I decide? Well, that thing is in that particular mask. The mask has that particular information. Where that N plus region has to be created, that information is there in the mask. So the end of the end of a digital design is basically results in a set of masks. The final end of all the digital design that you do is a set of masks. Because once you have that set of masks, you can take those masks and from that mask then follow a sequence of steps and create the IC that you want. So these masks are so if you want a custom design, then the masks are also custom masks because you want an N plus here and not here, according to your design. So it's a custom mask. And so these are what I was talking about, the masks that are there. And without these masks, you can't do, and these masks are for various reasons. They are, you can read on your own, very expensive. As I said, for 180 nanometer, it may be 100K. I think I have another chart here, which gives you the cost here. So this is from this particular site here. So you can see the cost of the masks because of the, the technology is moving to shorter and shorter dimensions. You can see the cost of the masks, how they're escalating. So here roughly you have, I think 1.4 million for masks here. And then this is 28 nanometers. So then as you go further, the mask costs are really increasing. Okay. So the masks are very expensive. Masks required to make your IC are really expensive. You can't afford them. Okay, unless your volumes are very, very high. So you can't have a dedicated IC here. So suppose there are a large number of users, each demanding custom IC solution, but in low volume. Right? Large number of them are there. Huge number of them. Each person wants, even a student, PhD student is, let's say, doing his project and he wants to control the stepper motor and all that, wants a dedicated IC. Right? So you're looking for a solution. And as a PhD student, you want 5 pieces or 10 pieces, right? So there are large number of users, each demanding custom IC solution, but in low volume. Well, the solution to that is design a general purpose digital IC, which each user can customize for her or his application. You can't design a dedicated IC which does that fixed job that you want. That I can't do. But the solution could be that let me design a general purpose IC. And the important point is a general purpose digital IC which each user can customize for his or her application. Then you know that each person may require 1,000 pieces, but now there are thousands of such users. So I can sell millions of such general purpose digital IC. And millions of such general purpose digital IC, which means that my cost will come down. Okay? So that's the potential solution. You can't design a dedicated solution for each person, but what you can design is a general purpose digital IC. Have we seen examples of this? So what we are looking for is, again, for our toy example, that what we want to do is, somebody wants to do this, somebody wants to do this, somebody wants to do this. Well, let's design a general purpose adder subtractor IC. Okay, so this is what we'll do. We'll design a general purpose IC, which this particular user will come in and customize it. And so it will do this particular task. The second user will also take our IC and customize it and will do this. The third user will also do this. Right? We have a general purpose adder subtractor IC. All right, so that's what we'll do. Now, have we seen something like this before? Let me, you guys have gone through EE210. For example, if we take from the analog world, somebody wants an amplifier with a gain of 20. Right? So with a gain of 20, so you go ahead and design the amplifier. Somebody wants an amplifier with better bandwidth and all that, maybe you design a cascade amplifier. Somebody wants another amplifier, so you go to a more, this thing here. Now designing an amplifier, you have seen, it's not trivial. Right? It's not trivial. It requires effort to design. Not only that, how would you design these amplifiers? Well, you have to take a transistor and you'll have to put it on a PCB with resistors and all that. It will occupy a certain amount of space, right? So we have all these different users demanding different kinds of amplifiers. Some 20, some 100, some with more bandwidth, some with less bandwidth and all this. What is the solution? Custom IC for each one of them is too expensive. A custom IC consisting of these bipolar transistor and 4 transistors and capacitors and all that will be very expensive. So a custom IC solution for each one of them will be very expensive. Right? But each one of them would benefit from a custom IC solution. So what is the solution here? Solution that all of you have seen. Huh? Op-amp. Op-amp was the solution. Let me make a general purpose amplifier. A general purpose, fairly complicated amplifier, which I can sell in millions. And now this guy who wants a gain of 20 comes in, and how does he customize the solution? He takes the op-amp, and the customization is done by adding 2 resistors. 2 resistors of appropriate values. Now compare a designing of this amplifier versus this. All that you have to do is put R1, R2, 1K, 10K, and you're ready with your design. So this is an example of that different users want different characteristics of their amplifiers. A dedicated solution is not possible. A dedicated IC solution is not possible. So what the industry came up with is, well, design a general purpose amplifier, a very general purpose amplifier, here high gain, high bandwidth, and all of those things that are there, and each user comes in and customizes it. To make not only amplifiers, you see here an amplifier, if I put a capacitor here, it becomes an integrator, all kinds of things that you can do with a general purpose a analog IC. With that, you can do lots of things here. So it's the same principle that we are talking about here. Same principle that I'm talking about in this case here. That different users want different dedicated digital hardware. And I can't, industry cannot supply that. A design for each, unique design for each one of them. So we come up with a general purpose IC, which you can customize. Okay, so that's the whole idea here. So let's look at now what is our general purpose solution. So this is our general purpose IC EE370 L8, right? Okay, so our IC has, it's a digital IC. So of course it's, we have, we'll just do 4 bits. So 4 bits here, and we can apply input here, and we can take output here. Okay, 4 bits and maybe 5 bits. So let's not worry about the number of bits and all that. 4 bit here, 4 bit here. It's a sequential digital IC. We'll need a clock, and of course for all the transistors and everything, we need a VDD and ground, and we add a reset pin. Okay. Now, remember what this IC is going to have. It's a general purpose system, and we are saying we are modeling our system as an RTL system here, right? A register transfer level. So obviously it will have a set of registers and some unit there which processes the data. If it could do multiplication also. So what these are not, so what I'm going to have in this IC are 4 registers. A, B, C, IR. Okay. This is not a unique solution. You can come up with many solutions on your own. So we'll have 4 registers, A, B, C, and IR. We'll have 1 adder subtractor block. Okay, because we are only interested in adder subtraction. But note that with adder subtractor, I can also do multiplication, repeated addition, and all that. I can do all that. So I have this one here. Now, it's a general purpose solution. So what my IC is going to do will be capable of doing is a series of elementary operations. My IC will be capable of doing series of elementary operations. What can my IC do? Well, let's suppose my IC can do these elementary operations. Remember, these registers are the A, B, C, IR. So what I can do is, suppose I design my IC so that it can do this operation. I can load something in my register A. Load means whatever is at the input X, I can load it in A. It's an elementary operation. My IC is capable of doing that. I can load in B. I can take X and put it in B. I can do that also. I can move things around within my IC. So whatever is in A register, I can move it to C. Or whatever is my register B, I can move it to C. I can move things around in my registers from one register to the other register. So I can read from the input. I can move things around inside my register. And I can also add things up. I can add up the contents of these 2 registers, A plus B, and put the result back in A. I can subtract the contents of A minus B and put the result back in A. And I can think of some more elementary operations here. So what I'm going to do is design my IC such that it's capable of doing these elementary operations. Now note, you can realize why am I choosing these elementary operations. Remember, what I want to do is I want to read in numbers A, B, C, D, and I want to do A plus B plus C plus D, or A plus B plus C minus D, those kinds of add subtract operations. So that's why one has chosen these kinds of elementary operations. So if my IC can execute these elementary operations, then perhaps I can do whatever computation you ask me to do in terms of adding subtraction here. So these are my elementary operations. Now how am I going to execute this? Right, so this is what remember, dedicated IC wanted, custom solution was this. And let's say my IC can actually do this, can execute this series of operations. How it will do it, we'll see in a minute. So how can I do this here? Well, perhaps I can do this way. I can load A, I can load B, which means I'm loading from, so what will happen is, inputs are coming on X, load A, load B, add AB, Then I'll load B again, add AB, then load B again, add AB, then move C into A. Output will be available in C. So what we are saying is that this thing that you're seeing here, and then of course it will go back again into this, to the first operation here. So my point is, whatever you want to do computation now can be broken into these elementary operations that are there. So my IC will do these elementary operations, and your solution, what it will do is implement your solution by using a set of these elementary operations in particular order. In some order here, you can repeat it and all that. As many times you can have any of these operations here. And so you can express your solution in terms of these elementary solution steps here. Right? So it makes sense. So all that I need to do is design my IC such that it can do these things. Okay? Now let's say load A has I give a certain bits to it. Load A is 001, load B is 0010, move C is 0011. So I assign some bit pattern to each one of these elementary operations here. Okay. So in a way you can see that what are these elementary operations? These are like instructions. Load A is an instruction to your IC to do this operation here, X into A. It's an instruction. Load B is also an instruction. So what we are talking about is that our general purpose system, digital system, can execute a series of instructions that are there. It can execute this instruction or this or this or this or this or so on and so forth. Okay. Each instruction, of course, everything in your IC has to be finally coded in binary digits. Everything has to be described in terms of binary numbers for it to be understood and processed. So for example, we are saying that this instruction, let's say I describe it in terms of 4 bits 001. So every time, let's say your IC sees a 0001, while it knows that it has to do load A. Every time it sees 0010, it knows it has to do load B. So like that we have this here. So now how do I do this? How do I actually execute it? So what I do is at X, now note that at X, I have to give not only the input, A, B, C, and D. I have to give not only the input, but I also have to tell my system which instruction to execute. Right? I have to tell that also, which instruction to execute. So suppose I do the following. Using X, I give both. I tell my IC to which instruction to execute, and I give data also, whatever data is required here. So suppose I do this. At X, and let's say everything is with the clock cycle, it's synchronous. So everything comes with one clock cycle. So input X, I give 0001. 0001, so the first, let's say 4 bits are an instruction. So 0001 means load A. So this goes into my system here. Right, system A. And next what I do, I give data. Next what do I give? 0010, instruction. And then I give corresponding data. Then I give 0101. 0101 is what? Add. It does not require a data. This operation does not require a data. But to keep simple, what I'm doing is instruction, data, instruction, data, instruction, data is giving. So I leave it blank. Doesn't matter. Your system will ignore this blank here. Then I give 0010. I load B here. Then I give data. Then 0101 add. And then blank. And then 0010 again load. And then I give data again. And 0100, the result is moved to C. And let's say C is the place register which is connected to the output. Okay. So you can see that what happens is these are the elementary operations that my system can execute. And so what I do is I give the instruction here and I give the data here right from X in a particular sequence. So my system knows that it's receiving instruction, data, instruction, data, instruction, data, instruction, data. Right? If I give this here, now your system is, if it can execute this, will go ahead and execute this and will produce the output at C. At C, the output Z will be available. And after that, what I can also do is the system, let's say after going through all this, goes back here. We have not done that. We can do, for example, add an operation where you reset everything. So what we can do is we can add a instruction called reset. So it sets all the registers to 0. A to 0, B to 0, C to 0, D to 0 here. So after doing all this operation, you can do a reset and then go back to the first stage here. And then it keeps on looping, right? Keeps on executing. So thereby, by using these elementary operations, we have executed this particular custom task that you wanted to do through these elementary operations. Now I can take something else, A plus B minus C minus D. You know that I can write this such that it executes that also. I can take something else, A minus B minus C minus D. I can execute that also. So I have a general purpose system which can execute any of these things that you can write. By how? How am I customizing? Well, through the input that I give. And in the input, I have both the instructions and the data. So by giving a suitable set of X here, I can make this machine do what I want and produce the output that I desire here. I'm giving X here. So how are they executed? We'll see. We are not talking about what happens inside, right? Right now, all that we are saying is it can execute these instructions. Those things we can do. All those design issues and all that we can do. All that. So, as I said, the point is not that this is a very nice system. The point is that it's illustrating what we can do. How we can construct a custom solution through a general purpose digital system. And what is this general purpose digital system? This general purpose digital system is one that can execute a set of elementary operations, a set of elementary instructions. So you supply these instructions and you supply the data, and your general purpose system will, depending on in what order you supply these instructions, will do a set of computation and will produce the output that you want. Okay? Yeah.
Data is ABC.
Data is?
ABC.
Data is, you supply A first and then B first and C and then D and all that data that you supply here.
First we have to supply
instruction. So in our design, instruction and then the data. Which data? Maybe you can supply A. Then instruction and then supply a data. Which data? B. And then you are adding it up, blank. Then again an instruction, and which data are you supplying? C. And then you are adding up again, blank. And then instruction again, which data are you supplying? D. And then you are adding up again. And then you're moving the output to C, 0, 1, 0, 0. Moving to C. C is connected to the output, right? And after that, maybe, as I said, what you can do is you can have an instruction here, which can reset everything. A, B, C, D, everything reset and goes back to the first stage, right? So it goes through loops. The digital system, we know, goes through state S0, S1, S2, S3 and comes back to the first state and keeps on looping. And so whatever instruction you give, it will accordingly do. Whether you want to subtract or add or whatever, it will do according to what you give. So the machine does what you tell it to do. But then you have to express yourself in these elementary steps. You don't have complete freedom. But if you choose these elementary operations carefully, then whatever task you have, you can express it in those elementary steps that are there. So these are the instructions that your machine can understand. Okay? All right. So let's look at this one here. So how do I execute this? Well, I may execute it like this here. So I remember what I said. My system has 4 registers. A, B, C, and IR. Why did I choose the term IR? Instruction register is the place where instruction comes in. So what happens is, in my state S0, what I do is I read from the X and I store it in my instruction register. The first one is an instruction. IR equal to X in state S0. Then when I come in state S1, I test what is there in instruction register. Remember, we go back and said each instruction has a certain bit pattern. 001, 0010, 0011. Each instruction is coded in a particular manner. So now, in the next step, what I do is in S1, I test what is there in my IR. And according to what is there in my IR, I generate a set of control inputs which will cause this transfer to take place. Data to A, or A plus B to A, or A to C. All these operations will take place depending on what is in the content of IR. Okay, and after I execute this, I go back and then load again the next instruction. And I keep on doing it. I've not added the reset step on all that. We can make it more realistic, but that's all. That's all. It reads an instruction, and then it goes to the next state, looks at what the instruction is, what the value of IR is, and accordingly does this. This is what we said as a melee machine. A general state consists of a state box where you may have some unconditional statements. You don't need to test anything. If you want to transfer something, you can do that. And then you have conditional statements. So that's a general purpose system here. Okay, all that when I put a state box, it says I've gone to a next state. Okay, I've gone to a next state. I'm testing a condition and then doing this. So this is what my system. If I have a system like this, it will execute these instructions that you see. Of course, I have to accordingly, A equal to data. I have to generate control signals and all that to carry these out. A equal to A plus B or C equal to A and all that. Okay, how do I implement this? So this is what we have now, a general purpose arithmetic system. Let me call it a fancy name, arithmetic system here. And 4 registers are there, A, B, C, IR, 1 adder subtractor block. These are our elementary operations here. This is our ASM chart of how it will execute these operations that you see here. All the details are not given, but this is our input X. How will I execute now? What will my data path look like, and what will my controller look like? So for example, data path, as I said, how do we construct a data path? All right, our data path will have all these 4 registers, A, B, C, IR. So I put A, B, C, IR. Has an adder subtractor block, so I put an adder subtractor block. Adder subtractor block has a select signal to decide whether I do addition or subtraction. Okay, there's a select signal here. Now, in many of these systems, when you have, remember, you may want to move the content of B to C or B to or C to B back and forth, or B to A and all that. Is better instead of running, dedicated wires between 2 units. For example, if you want to transfer between B and C, you'll have to have a dedicated wire between B and C. Instead of doing that, dedicated wires between different blocks, what you have is a bus. One single data bus. The red one shows a data bus. Okay, a set of, for us, the data bus is 4 bits. So one single 4-bit bus is running through your system. So if you want to transfer anything to anything, for example, let's say I want to do this. Move A to C. Move the content of register A to register C. Now note that each one of these registers has 2 pins here, 2 select inputs, load and enable. Load, when you put a load signal, what it can do is it can take the data from the bus here and load it into this particular one. Okay, so that's reading the data into the register when you enable the load. When you put the enable signal here, what it does is whatever is the content here, it gets connected to the data bus. Whatever is the output of this register B gets connected to the data bus when you put enable equal to 1. Otherwise, the output of this particular register is disconnected from the data bus. Okay, example is, one can do that using what we call as a tri-state buffer. A buffer is what? A buffer is whatever you place on A will appear on Y. That's a buffer. But a tri-state buffer has an extra input here. So note that tri-state buffer, what does it do? If you put enable equal to 0, which means there's no enable signal, then the output is Z. Z means open circuit. Z is open circuit. But when you put enable equal to 1, then if it's 0, then it goes 0, and it goes 1, and it goes 1. So that's what is called as a tri-state buffer. Normal buffer is whatever you put at the input, the same appears at the output. Tri-state buffer has this extra input here. So it can go into these 3 states here, 0, 1, and Z also. Z is basically disconnected. Output is disconnected from this. So that's what I'm saying here, that when I put an enable signal, if I put an enable equal to 1, then the output is connected to the data bus. When I put an enable equal to 0, the output is disconnected from there. And with the load, I can load something into my register here. So each register has load and enable, load and enable, load and enable here and all. So how do I carry this operation out? Let's say I want to transfer the content of A to C. So what will I do A to C? Well, I'll enable what? The enable of A, enable signal of A, which means A is connected to the data bus. So the output of it is put on the data bus here. And C, what will I do? Load. And once the clock cycle comes, the content of A will be transferred to C. And if I want from A to B, note that the same data bus can be used to transfer from A to B also. And the same data bus can be used to transfer from C to B also. So I don't need dedicated wires. To transfer from one to the other, I don't need dedicated wires. One single set of wires run through my system, and through that I can carry out transfer here. So in all these complex digital systems, you will see that there's a data bus running through your system. Okay? All this here. So can we see that this particular system that you see here can execute these things that are there? For example, if you want to do the first one, IR equal to X, what will I do to transfer the contents in the first register IR equal to X? This is also a tri-state buffer. So what if I want to transfer the X into IR? So I will enable this. So when I enable this, the input gets connected to my data bus. So input becomes available here to the data bus. And then I enable IR. I load IR. Right? And so what happens is from X to IR, the data gets transferred. So that's how bring it into, Same. Yeah, I enable this and I enable this also. So once this signal comes in, this is available here. So in state, note that in state S0, this will be enabled and this will be enabled. At the end of the clock edge that we said, as it exits this particular state, the clock edge will latch those things. Okay. So the actual latching will occur at the end of this particular state. All right. So by doing this, note that I can load X into B, I can load X into A, whatever I want, I can load all of that. Right? And you can also see if I want to add A plus B, A is connected directly and B is directly connected here. So, and the output is connected back to the data bus. So I can take A plus B, add it up, output comes here and it's available here. I can load it into A also. Any of these operations that you see here, I can do it. I don't need more resources than this. A, B, C, IR, and add a subtractor. Maybe you can do with lesser resource. I'm not saying that you can't. Okay. So A, B, C, IR, and I can do that. Where do the contents of IR? Remember, IR decides which operation to do. So the contents of IR actually go to my control unit, the state machine controller, because the controller will say now, controller will generate signals for this, whether this operation takes place or this operation takes place or this operation takes place. So all these contents of IR will go there in the state machine controller. And the controller will send back signals of these signals here. Add, enable for each one of them. And all this here. So the controller will send those signals to cause these things to happen. So you can see here, I've not drawn the controller. The controller will simply go from, I think in the next, maybe I have S0, just goes through S0, S1, 2 states, that's it. But generates a lot of control signals. Control signals here, all these control signals. I have how many? 2 into 4, 8, 9, and 10. At least 10 control signals you can see here. Have to be sent here to carry out these operations. Right? So a general purpose system here, which can execute these elementary operations. And how do we execute these elementary operations is described here. In terms of these are the resources that I use. A, B, C, IR, add a block here. This is how I connect them up. And this is how my system executes. Okay. I should add here a reset and all that, so reset, after you do all this, you should reset all the registers. A equal to 0, B equal to 0. I've not added that here. So what we end up with is the following. Now, this is a little bit inconvenient, as you must know. If I want to do some computation at X, I have to supply the instruction and the data, and all that, and go back and keep on supplying this. How do I do that? How do I supply X? I want to do some multiplication or whatever. How do I supply this? Now, you'll note that this is more convenient if I do this. This is more convenient in the sense the following. I don't supply directly, sit down and supply. I can't do that because the whole system has to run at a clock rate. Otherwise, you'll slow it down. So what I do is, this is my general purpose system here. I add a set of registers here, external registers. And this program that you see here, this instruction and data, let's call it a program. This program, I store it here in my registers, right? In my registers, I store this program. So where does this X really come from? So first, what I do is, I have this memory here, a set of registers. First, I load this up, program in my memory. I load it up, the whole thing. Okay? I load it up here in all of this here. So once I load it up, then I let my system run. And what does my system run? Well, it has to take the data X. This is the output. But from where should it take the data? Well, I have to modify my system here so that it provides an address. Because note that it's a series of registers here. For example, if I have 16 registers here, then I need a 4-bit address to decide whether I should take the data from here or here or here or here or here. This IC should supply the address. So note that if it supplies the address here, then what will happen is, once the address is available here, the address is decoded and one of these things are enabled and it supplies the appropriate X here. So this is a better solution than sitting here and somehow making an arrangement of supplying X. Right? How would you supply X? With instruction and data and instruction and data, how would you do that? Right? So the idea is that your entire program that you have, you store it in an external memory. And then interface that particular memory to here. And now your general purpose system, digital system, not only reads the data, but has to supply the address. It has to take X from an appropriate place. So I have to a little bit do modification here. Okay, so the same clock that is here, same clock runs here, same clock everywhere. So maybe what I do is, to supply this address, I add another register here in my system. And I call this register program counter. Program counter. Why? Because program, it tells me where the program, it sort of counts. It goes, remember, it will go from first register to if it's a 4-bit address, so the first one will be 0000. The next one will be 0001 and 0010. So sequentially it goes through. That's why I call it a program counter. It's like a counter. It goes from 000, 001, 0010, and like that it keeps on going. And it will start from the first register, and let's say I have a stack of 16 registers. So it starts from first, goes to the 16th. So my program counter will go from 0000 to 1111, and then come back to the first state itself. Okay? So I add a program counter here, and I modify my ASM chart here. So note that after I read an instruction, what I do is, I increment my program counter, which says, initially, let's say PC was 0000, right? Then I make PC equal to PC plus 1. So PC plus 1, the output of PC, note, it goes to the address here. So in the next one, PC is PC plus 1. So if you're reading a data, you're reading from the next one. And then again, so program counter is incremented in every state. So thereby, now you can see here, by adding a program counter, I'm able to now supply the address here and then read from an appropriate place here, from the memory. So this is a more general purpose system here. And this is what my system goes through. S0, S1, when it goes from S0 to S1, it has to generate some control outputs here. And when it comes back from S1, note that it's going from S1 to S0. Depending on the instruction register contents, it has to generate some control outputs. Control outputs are all the inputs that you see here. So what have we arrived at? Actually, we've arrived at a very simple microprocessor. What I'm calling as a general purpose digital system is nothing but a microprocessor. What is a microprocessor? Microprocessor has a set of instructions that it can execute. And we call that, whatever set of instructions it can execute, we call that the instruction set architecture of a microprocessor. ISA. Different microprocessors will have different set of instruction sets that they can compute. That's what a microprocessor is decided by. Each microprocessor does what with an instruction? Every microprocessor that you'll do, it will fetch the instruction depending on the address given by the program counter. Almost all microprocessors will have a program counter. It will fetch the instruction, address given by the program counter. It will decode the instruction, execute it, store the result, increment the program counter, and go back again. That's what a microprocessor keeps on doing. Depending on the instructions that are there, fetch the instruction, decode it, execute it, store the results wherever the results have to be stored, back again, fetch the new instruction. Okay? And so this is what is called as the instruction set architecture of your microprocessor. What are the instruction sets that your microprocessor can execute? How does it actually execute each one of them, clock cycle by clock cycle, and by what means, is called the microarchitecture of the microprocessor. This is the microarchitecture. This is how it executes these instructions. Okay? So, in a quest to come up with a general purpose digital system which you can customize for different applications, we have naturally arrived at the concept of a microprocessor, where microprocessor can execute a set of elementary operations, and the user writes a program, stores it in a memory, and the program tells which instruction to do in which order, and thereby you do the computation that you design. Okay, all right. So this is our very simple microprocessor, but a example of a better microprocessor. This is like a toy example. Is a microprocessor which is simple, but at the same time captures a lot of things, which is the 8085 microprocessor. 8085 microprocessor, first produced in 1975 or 76. Note that this it can run depending on who makes it. The first manufacturer was Intel, and then others also started making it 3, 5, or 6 megahertz. Uses NMOS technology. Minimum feature size, gate length was 3 micron. It has an instruction set of 246 instructions are there in this whole microprocessor here. 6,500 transistors here. All right. Since time is limited, I'll go and what will this microprocessor have? Let me show you. I managed to get some very nice photographs of this. So we'll come back here. This is interesting. This is the chip of the 8085 microprocessor. So somebody actually I found out that took a microprocessor, took the cap off, and could take some high resolution images and all that, and has put it on web. So I could locate that. So you can see the 8085 microprocessor. It's a 40-pin microprocessor. And you can see the data bus in blue that I've drawn here. Data bus is running here. All this that you see here. Data bus. This is this micro, it's very, not very, but to some similar to the one that we just designed. That it will have we had adder subtractor block. It has a ALU, arithmetic logic unit. It can do adder, subtraction, and or different kind of logical operations and all that. Shift right, shift left, and all that. So this is the ALU that you see here, arithmetic logic unit. This is a register file, the set of registers which are there. A, B, C, D, H, L, and all that. All the registers are here in this particular part here. And data bus is here, running through this. The IC pins are all around here. And this is the control unit. Your state machine. State machine is all here. Instruction register is here. So state machine is where, all the, input from the instruction register comes into the state machine, your controller, and the controller generates the control signals for the rest of the chip. Right? So this is a fairly complex, you can see here in terms of area, fairly complex unit here. And this particular picture doesn't show, this is the address bus that runs here. I've not shown it fully here. Address bus, which is because registers and all that are there. This is a separate picture of an early microprocessor 8008, even earlier, I could manage to get. So note that besides your address bus and data bus and all that, the VDD, the power has to go to every transistor, right? You have 6,000 transistors. VDD has to go to every transistor. Ground has to go to every transistor. So look at how VDD goes here. These are the power lines. Can you see the power lines that are, the VDD starts from here. Note how VDD is distributed. It doesn't show all of them, but it's distributed all over the chip here. And this is the ground. Blue one is the ground here. How it goes, it has to go everywhere. So you have to design your power distribution system, right? A power distribution system to, 6,000 homes, right? There's 6,000 transistors are there. And a ground also to all of them. Now remember also you'll have to supply clock. Clock has to come in, and most places are clock systems. So the clock has to come in from somewhere and has to go everywhere. Clock has to be supplied everywhere all over here, right? So it's not just the data bus, the address bus. So you have a VDD, you have a ground, you have a clock which has to go everywhere inside your chip. Okay? So let's stop here and then we'll continue.